Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Today we are going to be doing, I think I'm going to play around with a couple things in the lighting right now. I've gotten the architecture to a place where I'm pretty happy with it actually. And so now we just start working on like turning the crank on variance and speed. And so I've got some ideas about how I want to do that, but we've got a couple of different things I want to try there. So specifically the two things I want to try today, which I don't know if I'll get to both of them, but we'll get to both of them over the next 2 days, hopefully, is I'd like to try playing around with not casting the entire hierarchy, basically things that are far away, treating them as more aggregate elements, for example. I'd like to play around with that a little bit today. And then the other thing I'd like to do is I'd like to put in something where we can draw our hierarchy. Because again, right now, because we were still trying to lock down how we were doing our light transport, which I think now I'm pretty happy with. What I'd like to, I had never really gotten to the point of let's look at our spatial hierarchy and see if it's actually doing the work we think it's doing and if we can improve it, et cetera, et cetera. We never did that, right? So we just threw one in there and we're like, okay, we know we need a hierarchy in here, so let's put one in, but we haven't actually gone and really done much with it. So that's another thing that we have to do. So those are the two things we're going to be doing. Today is day 429, so day 428 source code is what I'm looking at here. All right. And so then as of last week, we had gotten to the point where we were pretty happy with how the light transport was stabilizing. I think we are still, I think we are still using a high number of bounces, if I remember correctly. Because we're in, let's see here, ray count, oops. You can see here that we cranked the ray count up to 256, and if we take a look at what's happening here, so this is a pretty slow running versus game, even though this is optimized, you can kind of see that the lighting is actually pretty stable here though, with the way things are going. So if this were running at 60 FPS, we would probably just call it done. And so the real problem here that we're looking at is just the fact that we can't get that stable of a variance without the speed hit. Now, we certainly can just go ahead and crank up the ray count to something like 2d6 and then do like more parallelism and more optimal calculations. That would probably be fine for this scene, but then again, once we start adding more stuff into the mix, it becomes more problematic, right? So when we drop the ray count down to something more manageable, such as this, and now you can see that we are running more we're running at 60 frames a second here now, and this is totally acceptable frame rate, but you can sort of see how we get this flicker in there. Now that flicker, you know, you could always just say that all the lights in the game are fire and they have a natural flicker to them. You can solve problems in tech with fiction, and that's always fine too. I don't discourage people from doing that because, hey man, it's all black arts when we're trying to do things like simulate lighting or things like this that we know to be intractable problems at 60 frames a second currently. Anyway, everything's an approximation, so whatever solution you want to use is fine. But, at least for the time being, I'm not going to go ahead and go that route yet because there's still a lot more we can do here to try and work out what we're, to try and improve the stability of the solution. And so I'd like to go ahead and do that. And so that's mainly what we're talking about here, is going ahead and figuring out how to continue to improve upon that, sort of that stability and just making it more clean. So a couple of things we can do. And let's talk about what those are and the things that I want to sort of get underway here. I'm going to load up Milton. Which, by the way, Milton's been awesome. Ever since that they found the bug in the what's that thing called? Pen. There's some kind of pen thing that it uses. I think it was from Papaya originally. I'm sorry, I don't remember what it was. But ever since they found the bug in that, Milton's been super stable. Just a pleasure to use. It's nuts to think about how... I don't even know, can we look out here? It's nuts to think about how big this thing is. Is there a way to zoom level 111 is what we're on, I guess. It's nuts to look at like how much stuff this thing does. It's like super good and it's very fast. Like, think about all this stuff that's in here, how much pen strokes there are, and it just kind of handles it all. It's just a good program. I think that, I don't know. Sergio did a fantastic job getting this thing going. I mean, look at all this stuff, and it just kind of runs right through it. It saves incrementally perfectly, too. There's no lag on save anymore. This is a good program, you know? It's just a really good program. Look at that. That's great, you know? Very, very well done. Anyway, let's go back here. There we go. So I just want to talk about some lighting mods that we could make. So let's talk about a couple of these here. So one thing I talked about is stratified sampling. Let's talk about that. 2. Multi-res sampling. And number 3, I think I mentioned this before, is bidirectional. So we've got a number of different things we can be doing here that, again, these are not optimizations in the, I'm going to go ahead and try to save cycles specifically on some given algorithm sense. This is more about algorithmic optimization. Just, can we be doing something smarter that works better, you know, and produces a more stable result just by doing the math differently, right? Or whatever. So let's talk about stratified sampling. So right now what we're doing is, on any given frame, if we imagine the hemisphere, and I'll draw it in 2D, but obviously it's actually 3-dimensionals, right? So it's actually a proper hemisphere, not a hemicircle or a semicircle. So if you imagine we have a surface with this normal, and we go to sample it, I mentioned this briefly the other day. Right now we're using pure white noise. And, you know, I'm going to even put that in quotes because we're not even really using that. If you remember, we've never really even gotten a proper random number generator in here. We just have a table, right? Because I just said we'll deal with random number generation later because we want to kind of talk about that as a topic. So, you know, we're just using this table, and that's not a very good way to do it because the period of this thing is pretty short, right? Now, we don't know that that's necessarily a problem for us in practice right now, but that could be too. So using a proper random number generator that we have some more guarantees about and that has a longer period might be helpful. But even if we had proper pure white noise that we actually measured and knew was good as an input, white noise might not be the best thing for sampling the incoming light. Now, why? The answer is because white noise is a completely, truly random in the semantic sense of the word. So when you say random, what you're thinking about in your head is no coherence, no correlation, no properties at all, right? You're thinking that from one to the next, the information you're getting out of a random source, you can say nothing about it relative to the previous thing, right? It's like cryptographical randomness in a sense. You're talking about something unpredictable. We can't say anything about it. Now, a good white noise generator is something that is very close to that. Now, we know that we can't really get true unpredictable stuff out of a deterministic machine. So unless we use, for example, the RD-RAND instruction or something like this on the Intel CPU, which maybe produces real randomness, I'm not really sure. I don't think they will tell anyone how it works. So I don't really know. But ignoring that fact, anything we're doing that's pseudo-random is obviously not truly white noise, it's not truly unpredictable, but its goal is to be as close to white noise as possible, as close to completely unpredictable as possible. And what does that mean? Well, it means that as the number of samples you take out of the white noise goes down, right, you end up with highly potentially biased placement on your hemisphere. Why? Because let's say we only take 2 samples, right? Well, intuitively, we know we'd like to take like 1 sample this way and 1 sample that way-ish. Because if we don't sample one direction at all, then we're very likely to have variance. Because we're just, if the light source was over here and we're shooting this way, we won't see it at all, right? So coverage is kind of important to us. When we're sampling this hemisphere, we need some coverage, a little bit at least. But what we know about white noise is it's not even remotely interested in that. A truly random sequence will just as likely pick 2 things here as it will pick a thing here and thing here, because the first one should have no relationship to the second one. Now, it's not true that maybe if you take any 2, it is more likely that 1 will be here than 2 in there, slightly more likely in white noise, because once you consider 2 at a time, it's different, right? But once you know that 1 is here, for example, that doesn't increase the likelihood that 1 will be here or here, right? It's like a coin toss. Just because you know 1 came up heads doesn't mean the next one is now more likely to come up tails, right? I know that's a little confusing, but that's statistics for you. Or probability, I should say. But the point is, regardless of how you want to think about the marginal probabilities there, the overall effect is that the algorithm does not overwhelmingly prefer an even distribution across the hemisphere, because by nature, a random distribution is not supposed to guarantee evenness. If it did, it would be much more predictable than white noise is, than randomness is, right? So what stratified sampling or other forms of biased sampling do is they say, look, we may want randomness for certain purposes. The purpose we want randomness for in this scheme is because we know we're not going to cast an infinity of rays or close to an infinity of rays. So we know that we can't use a complete coverage. So over time, we would like to get a complete coverage by randomly moving around the space. That's what we want the randomness for. But on any given frame, in order to retain a fairly good picture of what the lighting is, we don't want all of our casts to end up going in one direction. So we want to force the randomness to work within, say, compartments of the hemisphere, so that we know we're not going to be randomly clumping on certain frames, which will drastically bias what we think the lighting is on that frame versus on another frame where the distribution may have been more even. So stratified sampling says, let's make compartments of the hemisphere and force the white noise to be distributed over that hemisphere more cleanly, right? In a way that is less random, but perhaps better. So we are reducing the randomness in an attempt to try and make things more consistent, right? Now there's 2 ways we can do this. And stratified sampling isn't maybe necessarily the only word, right? So I've talked about blue noise in the past. So white noise is just dart throwing. Randomness, I don't know, I just get a bunch of points, right? Some of those points are very close together, some of those points are very far apart, and that's just how it goes. That's white noise. Purely random. Blue noise, on the other hand, once I throw down a dart, I restrict the ring around the dart and say no one can throw a dart anywhere in here, right? So what that gives me is it gives me a distribution where I know that all the points are somewhat separated. I cannot cluster around a particular area, right? Blue noise is not technically stratified sampling. Stratified sampling means random within buckets. So you can still have some clumping here in a stratified sample, right? Or you might not have clumping within the buckets, but you may say, well, I'm going to pick something random in this bucket, something random in this bucket, and the two things in either bucket happen to end up very close to each other because I'm not checking within the buckets, right? So stratified sampling and blue noise are actually a bit different. Technically, oftentimes stratified sampling does not indicate a minimum distance between points. Blue noise does. Blue noise says no 2 points can be closer than this, period. That's the definition of it, right? This is also called, for some reason, Poisson disk. Let me just get these up for you. I don't know. Is that? Yeah. No, it is a C. There you go. So what you can see here, these different kinds. So blue noise is the name that's used for this pattern of sort of random but not, if you will, that has points that are required to be a certain distance from each other. And the reason that this is an interesting phenomenon, for a lot of reasons, is because it actually came from the retinal cells. You can see them saying that here. Let's see. Oh, Don Mitchell is here. He was the person who originally taught me about blue noise, in fact. Anyway, he was an AT&T guy. He then went to Microsoft Research, and he's retired now. I haven't seen him in a while. I tried to email him actually 2-3 years ago and never heard back. I hope he's doing okay. Anyway, he's a great guy, and he was the one who originally taught me about blue noise. And anyway, he originally started looking into blue noise specifically because it's the way that your eye, the cells in your eye are set up, and it helps eliminate regular patterns. Because if you imagine setting up the samples for things in your eye, oh, we're getting off topic here, but this is interesting stuff to me. If you imagine the way that your eye works, right, it's essentially like a photograph plane, where you got an image that's going through a lens, like light that's going through a lens, and it's hitting this sort of film back almost, and the film back is your retinal cells, right? And they're sort of developing the image, if you will. They're taking the light that comes in, and then your optic nerve is like counting it, right? It's saying like how much of that light is hitting it. If you imagine placing those cells regularly, if they were highly regularly set up, right? Then what happens is as a shape moves across it, as the light moves across it, you would see regular patterns like stair-stepping and stuff like this, because you're always going to do sort of that linear filtering between the two as it moves from one to the other. You're going to see these sort of regular stair-stepping patterns as a shape, for example, that looks like that. You'll see the sort of gradual regular pattern of it getting dimmer, 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 dimmer across each row, right? If instead they're set up in a blue noise pattern, like this sort of thing, then because you now don't have any particularly regular way, because it's always a little bit random, you'll always get some noise in there that makes it so you don't see repeating patterns, because there is no way to construct a repeating pattern unless the thing that's coming in is the exact blue noise complement of the cells themselves, right? Which never happens. It's not really possible, right? So essentially what a blue noise pattern does is it makes it so that you get the most pleasing anti-aliasing possible on your image, because nothing can produce a regular pattern for you to pick out. So blue noise is in effect the holy grail of sampling pretty much always. It's always what you would use if you could. Now, it's much harder to generate than anything else because it's by default something that only is defined by a constraint applied to white noise, effectively. It's basically saying take a white noise pattern and remove all the points that are too close. That's kind of how it's defined. And you can generate them in quicker ways. In fact, I talked about that in my articles on how the witness grass planting system works, which I always meant to do a second update to, because I actually updated the witnesses grass planting system subsequent to that, but that's a whole nother story. Anyway, so what we have here is kind of an argument for what we want to do optimally, which is if we could sample these hemispheres with a nice Poisson disk or blue noise pattern, we would be the happiest possible people, because then we would sort of know that we were maximizing our samples, right? Maximizing them from a perspective of not knowing what we're aiming at. Now, there's this concept of importance sampling, which is to say that we may not really want to cover things uniformly. It may be that we know we should cover things more in one direction or another. That's a separate issue. That's sort of saying that if we have information about where we're likely to get more signal, maybe we should aim more heavily there, right? And that's fine. But what we're talking about is, in the absence of the guidance, or even once we have the guidance, how do we then distribute our samples along the area that the guidance wants us to use, right? And the answer is always blue noise if you could. You'd always use a blue noise pattern to sample if you could. Again, blue noise potentially adjusted by some bias if you know you want to shoot one area more heavily. You still want blue noise, but you just kind of shrink so they're closer together towards one and further away towards the other. You would still use blue noise because it's always better, pretty much. You never really want white noise. So, given that fact, how would we do this in practice? How would we get something that was going to do the stratified sampling? Well, we've got two options. One is we can really do blue noise. And if we want to do blue noise, the cost there is that we can only have a limited number of patterns. The other is that we can do stratified sampling, and then we can do random every frame. Now, what do I mean by this? Well, let's suppose we want to do stratified sampling. It's trivial, right? All we have to do is define how we're going to talk about coordinates. Let's say we divide the hemisphere into 4 pieces, and we just do white noise in each piece. Right? 2 white noise samples in each piece. There's some free stratified sampling, right? Maybe we take it a little further and we say, well, we've got a cone that's facing sort of outwards, like the main cone of interest, and then we've got sort of the area around the cone. So maybe we shoot, say 8, if we do 16 rays, maybe we shoot 8 out the cone randomly, white noise, and then we do, 4 around 8 around the cone by just picking white noise around each of the octants, right? So it's pretty easy to imagine how we would implement stratified sampling. It's not much different than what we have now. You just throw it in there and go, okay. Rather than just say pick any random thing on the hemisphere, we're just going to say pick something close to a particular direction on the hemisphere with white noise. And off we go. So a stratified sampling is pretty trivial. That's how we do it. But blue noise, very expensive to create. Much more expensive to create. So we probably can't create it every frame. But what we can do is say, what if we created, let's say, 16 different blue noise patterns? Maybe. And then what we did is just rotated them or something. Right? Rotate them randomly per place that we're sampling. Because a blue noise pattern, you can rotate it all any way you want. It'll still be blue noise. So we could do something like that, right? Spin it around the normal, those sorts of things. And it doesn't cost as much as you would think because it only costs 1 rotation. Like, all we have to do is construct the coordinate frame for the blue noise in a rotated fashion, which would cost us like 1 sine and 1 cosine, which is a little expensive, but it's not the end of the world. So, we could imagine doing blue noise by picking a random angle of rotation, so that part's white noise, and won't destroy our blue noise pattern, and does inject a fair bit of randomness. And then we have a few patterns if we need more than that. We have, a couple different patterns, let's say. I don't know. Maybe we don't. Maybe we just have one, and we just use randomness on it, right? So there are ways we can get blue noise into a real-time algorithm, even though we probably don't want to actually create the blue noise every frame, because that might introduce too much overhead into the system. we certainly can still get the benefits of blue noise if we're, or at least some of them, if we're willing to do some pre-computation and a little bit of setup. So which of those we want to do, I don't know, but you know, those are our options. We could probably try the stratified sampling one first because it's much easier, and then think about the blue noise one maybe a little bit later if we think it's worth it, right? All right, let's go to multi-res sampling. So multi-res sampling is, and unfortunately I kind of drew over the area I would have used to illustrate it. My bad. Pretend this isn't here. So multi-res sampling is just saying, well, okay. So, you know, I've got these reflectors. And I want to compute the lighting for a point. Well, okay. So I do a ray cast and I find that I miss these reflectors, right? So I'm in this part of the spatial hierarchy, and now I got to test against all of these, right? Because I missed these two here. If I hit one of these, great. I could stop early maybe. But now I got to test all the guys in this thing, right? Well, what if instead of doing that, we just said, look, when you get a certain distance away, let's say this is, you know, maybe this is the sphere here or something. When you get a certain distance away, like if the center of the thing is further than a certain amount from the point, just use an aggregate understanding of the lighting for this region as your output rather than testing the things in it. Right? Just compute an aggregate value. I don't know how. Just by an average of the light in the region. Right? Not my problem. I don't know how we're going to do it, but we're going to do something that produces an average value for each of our bounding boxes. And rather than descend through the spatial hierarchy, we will only descend into ones that are close enough, and ones that aren't close enough, we just use the aggregate value as the output. Done. Right? So that's something we could consider. Now, I don't know how much it will affect our results, but it's an example of something we could do. And this improves our variance potentially in two ways, actually. The first thing it does is it reduces variance because now you're using a smoothed average of a number of reflectors, which means that it doesn't matter whether I was shooting this ray or this ray. They're both going to get the same result back from this guy, right? And that reduces variance because now you're not talking about missing this guy and hitting this, right? So that you get two very different results based on a very small angular change. Again, introducing variance in the system. What we're saying is, look, we know we're never going to shoot enough rays to really capture what's happening out here because it's so far away. We'd have to shoot tons of rays in a really tight angle to capture all that lighting. Let's just figure out what generally that is sending back and use that. And this is very similar to the concept of voxel cone tracing, right? Which we know is used in high-end engines to do, you know, reflection kind of stuff and bounce lighting. It's very similar to that voxel cone tracing concept. It's saying, look, when we get further away from things, we don't need to know really specifically where we were casting. Because generally speaking, it's a tiny part of our hemisphere. Just give us the general light that's coming back. That's what we wanted anyway, and we're just never going to shoot enough rays to capture it. So if we can just smooth out those regions and just get the result comes back with one ray, it's pretty good, right? So that's what we can do with that. Bidirectional sampling, finally, is just the observation that right now what we're doing is we're saying, look, we find a path to transfer light between two surfaces right now, and then we only use one direction of that. We just say, oh, okay, so we know that light's going to get transferred from this point to this point. Why not just say, look, it transfers the other way too, right? And the reason, again, that reduces our variance is because for the same number of ray casts, we get twice the amount of light transport. So it's as if we cast twice as many rays, effectively, right? Now, it's a little bit cheeky of me to say that reduces our variance. We don't really know that it reduces our variance, actually. It could increase our variance for all I know. Because there's nothing that says it's going to really decrease the variance, because that transport could be an unlikely path, in which case counting it twice is worse than counting it once, in a sense, right? So we don't really know that that reduces our variance, but what you can generally say is that if in general we have set up the rest of the scheme to reduce variance in general, then using the paths more efficiently should, in theory, over the grand scheme of things, reduce the variance because we're just getting more raycasts effectively at that point. So if we generally expect an individual raycast to reduce our variance, then we would expect doubling the number of raycasts we're effectively getting to reduce our variance in general, as opposed to exacerbating it, right? On average. Again, not on any given ray may do the opposite of that. So it's hard to say definitively that that's the case, right? Okay. There we go. So I think that is most of what I wanted to talk about. And so those are the things that I'd like to explore. Now, we don't really necessarily have any way of predicting how these are going to affect us because, again, lighting is one of those nasty problems that's just very amorphous. We don't know anything about what the solution looks like unless we're casting, millions and millions of rays. And so when we're talking about casting such a small number of rays, it's really more of a hack at that point, and we have to explore our options in a very experimental way. We don't really know, when you get down to casting so few rays, you don't really know what you're dealing with in terms of the math, right? You can sort of try to do your best to approximate the real answer, but at some level what you're really aiming for is not the real answer anyway. It's sort of the smoothest answer that still has effects you cared about, right? So I think it's best to kind of remember that we're in that sort of uncharted area. So yeah, the other thing I can do right now is also say, if we take a look at world mode, and I'm going to go to screen index here, if I crank up the number of screens a little bit, just so we have that existing slowness, you can see that in this case we're running it at a much slower frame rate here when we get more of these into the mix. And if I take a look at the profiler, right, you can see that we've got 81% of the time spent in compute light propagation, right? So even in the case where we're only casting 16 rays per attempt, you can see that this still is pretty costly, right? Once you get enough stuff in there. So the thing that I'd like to try first, I think, is to see what I can do with the multi-resolution stuff. Just kind of interested to play with that a little bit. I'd like to see if we can get the multi-resolution stuff working. Then from there, we'll start looking at the stratified sampling, and then finally, when we're done with everything, I think I'll try to add some bidirectionalness to it. Right? That's my current thinking anyway. And then once we're done with all of that, we will be able to move on to the final step of lighting, which is distributing and using our lighting points effectively, which I think will be a really nice touch because it'll smooth out things like these walls. Instead of them having different lighting across them, they'll have a nice uniform light across them, which I think we want. Our game's look is supposed to be kind of overtly blocky, so at some level, I guess I'm not 100% sure that's what we want. But I do suspect it's what we want, because I think we want the art to emphasize the blockiness, not the lighting necessarily to emphasize the blockiness, if that makes sense. But, that's obviously up to us. We can always decide not to smooth it and use blockier lighting if we decide that that is a nicer look for the game for whatever reason. So anyway, I think that's where we're at. So let's go ahead and take a look at how we might do that. So the simplest way to do that is to go ahead and take a look at these lighting systems here. We've got this lighting block, and in it, it's kind of got a bunch of information, right? It's got a ref C and an emission and all this stuff. Right now, those don't get used if you're an aggregate lighting block. So if you were one of the lighting blocks that's just used for sorting, what you can see here is inside raycast recurse. Then what's going to happen is, as you're testing the faces of the array. What you can see here is that, in the case where there's two separate places where this can happen. In the case where you're inside a particular box, then obviously you just recurse. And that is always going to be correct, right? Like if you're casting from within a box, you're always going to go below it. So we don't really need to look at that case, but let's look at this case. In the case where we're raycasting against the box here, then what you can see is if we find that we hit a particular one of the box faces, then we recurse into it if the box has children. Now, what I'm proposing here is we say, well, okay, we've got a t-value, right? What we could do instead is say, if that t-value is greater than a certain distance away, don't recurse down the box, right? Just don't do it. If the t-value is too far away, let's just pretend we hit a box here and have that box be used in some other fashion, right? That's all I'm saying. Now, the problem with this that we see is that we sort of have once we have two different types of boxes, it becomes a little harder to figure out what the light transport is exactly. And there's two ways that we can do this. One way we can do this is just to set up synthetic lighting for these lighting boxes. And I think that might be the best way to do it. It's hard to say, but it might be, right? And so, one way we could do this is just say, look, let's just set up synthetic light indices. So much like we add lighting boxes, we'll add lighting points as well. Maybe one light point per side of the box, right? And then when we build the box, we will set those lighting points to be averages or something like this that allow us to send out the right average lighting out that direction, right? Just basic, simple, some kind of simple thing like that. Then what we would do is when we return one of these, we just return the box right here. It's the same with this. So it's almost, instead of box child count, it would just be an and. It's like box child count and we're close enough to the box. Then recurse. Otherwise, just return it, right? And that seems like a pretty compelling solution to me because it keeps the algorithm very simple. None of the code really has to change. The only thing we need to do to some of the other parts of the system is back where we actually do the lighting test routines, there are some places where we loop over our point counts. All we really have to do here is make sure this point count is not modified. So we'll add points in an extended sense. So we sort of have an original, like we have an original box count, we'd have an original point count, right? And we would just know that there are these additional points after it that we're assuming are not going to be involved, right? So I think we can just do that. Let me just verify that fact. But in here, for example, inside compute light propagation, what you can see here is when we go through this algorithm, all we do is we say, look, did we get a box back? If we got a box back, we just do our thing, right? So really, that's all we have to do. And yeah, that would be all there is to it. So I think that's pretty much it. There's nothing else that we would have to do. And yeah, it feels pretty straightforward to me. So I feel like that's the right solution to this. When we come in through Splitbox, and what we could do here is just have a U16 point count and a U16 extended point count. And so when we come through here and we set the point count, I could also say, all right, the extended point count equals the point count. But then I can add past the point count as we go. So yeah, so off we go. We do this point count. We seed the points and do whatever we want to do there. And then when we come in to build spatial partition for lighting, we just add points. So in here, for example, you can see us creating boxes. Here's an example of us creating a box, right? Where we do add box storage. And what we could do is add points now as well, right? So, you know, we could just add 6 points or something like that when we add one of these boxes, right? So maybe inside split box, that's what happens. Maybe that seems pretty fair, I guess. Let's take a look here. Yeah, so you can see here where we call split box recursively, we basically create the box here, and then we add the 2 boxes to it. And then in the case otherwise, we just record the box references here, right? So either we use the boxes that we get passed, or we put them in here, right? So what we could do for that is, I think, just again say, all right, if the source count is greater than 4, then we know this is going to be a, well, I guess in any case where we call split box, actually, we're going to want this. So I guess this just happens, period. Yeah, I think this just happens, period. So in any case where we called split box, we're going to need to create these. Yeah. So inside here we have, when we do build spatial partition for lighting, inside here where we do our root box, you can see us get the root box here, and then we split the root box. So that means every box that is that's not an actual leaf node that has actual light information will come through this path. And when it gets down to here, I think we just want to do it right here. So at the very end, when we know exactly what our child stuff is, then we can compute the lighting, I think, at that point. So let's go ahead and do that. So here what we're going to do is compute the aggregate lighting for this container box, right? Partition box. And so the parent box now, you know, should have a light, this light index here should be just garbage. There's nothing in it because it's never been used and never going to get used in the current version of the algorithm. What we're going to do is now start using that, right? So we want to just set these lighting indices to sort of be incremental. And this is kind of a dumb thing, but it's just what we have to do. So we've got 1, 2, 3, 4, 5, 6 of them. And what we're going to do, again, is just set them like so, right? In fact, we could do this a little more efficiently without actually doing the back reference by just doing this. Something like that. So we can say our light index equals the extended point count. Something like this. And then at the end, right? So we do something like that, which just assigns 1 light point per, you know, per side. So 1 light point on the top, bottom, 1 light point on each of the 4 sides, east, west, north, south. So there's the entire assignment, right, along the parent box. So we do something like that, then we, and I guess this one technically, we don't need one for the 6. The 6 is just the terminator. So we just assign a light 0, 1, 2, 3, 4, 5, like so. And then we're done. So now this has light points. But we need to actually compute the aggregate version of each of those, right? So we need to seed those with some actual information. Because now, if we look in here, there's information for each of those points. We haven't set it, though, to anything that we don't know any of these values. And we need to know these values for those points in order to do anything useful with them, right? So if you take a look in here, all of the initial points all got seeded with something, and our points that we've added will not have been seeded with anything. And so if you take a look at this code here, we need a way of replicating that for each of these light points. Right? But it's not this. right? We need to set all these values, but we need to have a different way of setting them because this is not, this is not useful, right? So we need to figure out a way to set all these values, and luckily we pretty much know at least one simple way to do it. Now there could be more, you could imagine a lot of different ways of doing this particular thing because the way that I'm going to propose doing it now is actually not very accurate and probably not very good. And so we probably want to investigate ways of doing it better. But, I'm going to just start with the simple one. So what I would say first is, look, here's what's happening. We've got some boxes, and now we want to enclose those boxes in another box. We did that spatial partition-wise, so that's all fine. But what we have to do now is say, okay, we want there to be a point, let's say here, and we want it to encapsulate how much light is generally leaving this box in this direction. So the simplest possible way to do this is let's just take all of the surfaces that are facing that direction and average them together. Right? Really, really simple, really, really stupid, not very accurate, but there you go. Right? Entirely plausible. So we can do that. Another thing we could do is weight it by how close they are to this. So things that are really close to this will contribute more because you have a higher chance if you're coming in through here of hitting them before hitting something else because they're closer. So we could weight by distance as well. Both of those two things. So I might do that, right? I might weight by the distance, but then, otherwise it's just an average. That's the simplest way. I think it's a pretty good way. It doesn't cost us very much to do, right? It will not affect the runtime of this routine hardly at all. There is another way we could do it. And this way is much more involved. But if we wanted to be accurate, we could do it. And what that is let's run the raycasting recursively, right? So let's take the things that are inside a box, which we know is something around, 4 to 8, I think. I'm not sure what a requirement is. No, it's 0 to 4. So if anything has more than 4 things inside it, it splits them, right? So we come through here, the root box has, whatever it is, 100 boxes in it or something like this. It says if it's greater than 4, then you need to split them into 2 halves, right? And create 2 boxes that have each 50. And then those will get split and so on. So actually it has between 2 and 4, right? It has between 2 and 4 in it at any given time, right? And it's a KD tree here, looks like, because it takes a dimension index. So it basically runs through and it's going to split. It's going to look, like this. That sort of thing, depending on the distribution of things. So if we know that we only have 2 things, or 4 things per box, you could imagine running a little raycast that just casts an additional, say, 64 rays or something around to see who can see which parts of the external box. And then you just actually do a raycast to figure out how much light generally is hitting this thing. We could do that, right? Totally possible. I'm not going to do it, because it just adds more computation to our system, and we don't know that it's necessary. But if we really wanted to try and get an accurate estimation of the light that was leaving, that's what we would want to do. And so we may find that this is just that averaging is just not an adequate substitute for actual light transport in our game most of the time, in which case we may have to do something more fancy that does cost more, but still not as much as actually doing the raycast entirely on everything all the time, because when you subdivide, again, it's much cheaper to do a raycast on 4 boxes than it is to do one on hundreds of boxes. So let's try the averaging version first, because I think that's the simplest, so we're just going to do that. So what I'm going to do is I'm going to step through the light indices for the box here. So I'm going to start with the surface index, and I'm going to loop through all the surfaces of the box, like so, right? So this is exactly equivalent, really, to how we're stepping through it here. And so I do actually also want to get the surface information out as well, just so that I can correctly set the location of this point, because people are using that location. Now, it doesn't really need to be set, because since we're only using that position as an average, it doesn't really matter as much. But again, you know, there's implications, right, in terms of how the normals work out and that sort of thing. So I'm going to try and set it accurately anyway. All right, so if we come through here, we need to know which lighting point we're setting, and unfortunately for us, that's pretty easy. It's just going to be the light index for this surface, because there's only one per surface. So all we have to do is just pull out whatever that one was that we assigned up here, and that's the one that we're going to set. We also know what surface we're on, but because we know that we're the parent box here, so we can just use this information directly, and then we've got it. Setting the point is pretty trivial. All we have to do is just take the surface P here and not modify it, right? Because I believe the surface P is just the correct P in this case, right? The reflected color here is just going to be the average of the ones underneath us, I believe. So we just need to loop through the boxes and average them. Oops. Let's also get our light index out here. I'm going to call this assign light index, just to avoid confusion of what's going on there. And I'm going to go ahead and get this light index out here, so we can use it everywhere. So that gives us a little bit of an in there, right? So when we go through this, what I want to do now is say, okay, I've got my individual light indices, so now I want to average. All the rest of the stuff is just going to be averaged together. Now, I don't need to know average, I don't need to know values for any of the other things, because I don't, well, so I'm not sure what we would want to do with average direction to light. I think it just doesn't matter, because it should never get used, really. So I think what I could say is, look, some of these things just don't matter. So what I'm going to do is just set it to be directly outward from the surface, right? Because I don't think we care. Similarly, like accumulated weight and stuff like that, I don't think we ever care what those get set to. And accumulated PPS, we don't care either, because I'm pretty sure all we care about is emission and initial. Also, I'll keep these cleared, but I don't even know that they would ever get played with. So we'll look at that a little later when we're done with things and see, do we care what these get set to? But mostly I think these don't matter, because since we don't ever use the results of this light and we don't cast from it, it shouldn't really matter, right? But these other folks here, these need to be average. So the reflected color, the emission, and the initial, those are the ones we want to look at people underneath us and figure out what they should be based on that. So that puts us into a loop here over our children. And you can see us up here with that information, right? So we have the child index. I guess we know it this way. So we know that this is our first child index. We know that our child index, our children run this way, like so. So we can go through our child indices here and just do our summation over all of our children. That may only be 2 children, but again, I'm doing this in a more general case here because we haven't investigated the spatial hierarchy much yet. We may not want only 2 children per box. We may want more like 8 children per box or something for all we know. So I'd like to have this routine be flexible and be able to work no matter how many children are in a box. Whether there's 4 or 2 or 8 or 16 or 100, it should just work. Because we're going to want to play around with the spatial hierarchy a little bit later as we tune the lighting, and I don't want to have this routine break at that point. So yeah. So now what I want to do here, and I guess I can pull this out because really that's happening at the end when we assign. What I want to do now is create those averages. So we have the ref-C, we have the emission PPS, and we have the initial PPS. Again, I don't know that initial PPS is really going to matter here. I don't think it really gets used. Emission PPS is really what gets used, so we may not have to do that one either. But I'm going to compute it anyway just because we don't know yet, and we might as well. It's not going to cost much to do, and we can always eliminate it later if it turns out we don't care. So what I want to do is set these based on the average, and we're going to use the same technique we've used everywhere else we want to do something like that, which is that we want to do the reflected, the emission, the initial, all as weighted sums that we then undo the weighting. You know, we normalize for the weighting at the end based on the accumulated weight. So we've got a total weight here, and then what we'll do is compute the inverse weight. Oops. At the end to give us our normalization coefficient, right? So then once we're in here, we know we want to take all of those surfaces that are on the same, pointing the same direction as ours, and we want to take those surfaces and basically we want to take all of those surfaces and average them together, potentially based on the distance that we are from them, right? So we know our point P is here. We know that we'll be getting other point P's that we're going to sum, and we can take the distance between them and use that as a scaling coefficient, right? So we want all of these to start out zeroed. So all these are going to start out 0. Then we go through the child indices one by one, and we're going to sum up the points that they have on this particular surface. So we need a child point index here, and we're going to loop over that. And then do that summation. So again, we need a distance, or a weight that we'll compute here. We'll add the total weight, like so. And then we will sum each of these based on that weight. So when we take a look at what these values are here, where we do the various weight summations here, and we do the total weight with the summation, what we need to do is we need to have a way of accessing the correct child points. But after that, it should be fairly straightforward because we know each of these points has that information on it. So you can see the lighting point here has like the ref-C, so I can just say like, okay, the child point ref-C goes in there. We know the solution emission PPS for the child point index gives us what we want there, and the initial PPS for child point index gives us what we want there. So that's pretty straightforward, and then we get the total weight, and off we go. So this is the entire structure of the routine. All we really need to do is know how to find this point. And so in order to do that, we need to get the box that we're talking about here, the child box. So we need a lighting box And for that, we're going to have to grab the box out of the box array here, right? Exactly the way that we were doing it right here. So that gives us the child box in question, and then once we have the child box, we know what its child indices are by just looking here, right? So we know that the child point, the point index that we're going to start with is going to be the child box light index for whichever surface we're on, right? So if we're on surface 3, we start at that light index, and then we know that the child point index has to go from there to the one that's in front of it, right? So the next one in the array, we subtract out the previous one. That gives us our count, right? Oh, no, what am I talking about? That's just dumb. This is just this. We know we go until the next one in the array. Yeah. So that's really all we need to do there. We'll loop over those points. Now we can get our actual child point out. This gives us the child point, and once we have the child point, we can compute the weight however we wish. I'm going to use that same function we used before, which is to say we're just going to take the distance between the 2 points and use that as a divisor. So I'm going to take the point that we're talking about and the child point, and I'll just use the distance squared, right? So the length squared between those points is how I'll weight them, and that's really it. That's the end of the story. Oops, I don't know how add box storage got deleted there. Must have been a typo, since we certainly didn't mean to. And these are U16s. So I believe that now when we run this, we are now computing aggregate box lighting. Now, again, one of the problems is we don't actually know that we are. And when we look here, you see the lighting solution. All we see is the total lighting solution. We don't get to see that spatial hierarchy. So what I'd like to do is I'd like to go ahead and see if we can now move to, again, computing the lighting now using that aggregate information is going to be trivial. Inside here, all we're going to do is just do a return if t force this case. We're going to add like 1 less than here, and that's all we'll have to do to use the multi-resolution lighting sample. So it's great, right? But if we do that, maybe it just works brilliantly all of a sudden, and it's fantastic. Great, yay for us. But chances are it won't work perfectly. I mean, right, we're dealing with complex stuff with a lot of interrelations and so on. We're not even going to know if we computed those values right, And so what I think we need to do is we just have to have a way of showing our spatial hierarchy in more detail. And in order to do that, we're going to need some way of sort of stepping through it somehow, right? And so what I want to do is just add some simple ways we can do that, hopefully, maybe inside output lighting points, for example. So in output lighting points, that's the thing that gets run when I hit the F1 key. So that's this thing. So what I'm thinking is maybe we can use this to our advantage here. So let's suppose we did output lighting points and we were going to do it this way where we go through the boxes, and you can see this kind of does a nice, it does nice work that way. It goes through each of the boxes and sort of puts the information out there. Now why that's timed I don't know, because it's not normally called, but I guess let's take a look here. you know, it doesn't really take any time, and it wouldn't be called normally anyway, right? Output loading points is right here, and it just doesn't get called normally. So I don't really care about this being a timed function. I'm going to get rid of that. And what I'm going to do here is I'm going to go ahead and say that this is going to have a recursive function now. And what I want to do is I want to make it so that inside here, where we output one of these boxes, we can actually choose to or not to descend into the sub boxes of that box. That's my general idea here. So what we're going to do is we're going to say output loading points recurse on this particular box, and then we're going to have a depth function here, let's say. And what I'm going to do is say, well, if the depth value is 0, then I'm going to do the thing that we were doing before, right? So we'll do the push of the lighting elements if the depth is 0. But if the depth is not 0, then what I'm going to do is just call this on the sub components, right? So we have one other problem I want to deal with, which is that we may not have any subcomponents. If we don't have any subcomponents, then I will let this case happen. So if the child count is 0, meaning, I'm sorry, if the child count, if the child count is 0, then I know that we can't recurse on this box. It doesn't have any sub boxes, so we'll do it. But if it does have children and the depth value that we're passing in is high enough, then what I'm going to do is I'm going to say, okay, let's continue downward, right? And so all I'm going to do here is take the boxes, and I'm going to do the plus child index here. And again, we also need to take into account whatever the first one is. But that's it. And then what I'm going to do is I'm going to pass depth -1 so that it will continue to reduce the depth as we recurse downwards. And that's all, right? That's it. So then what I'm going to do is I'm going to call output loading points recurse. You know, and I guess I don't know why I removed time function for this. I guess we can still time the whole thing if we want to. I don't know why we would, but we could. And so what I'm going to do here is just pass the things we need, which is the group and the solution. And then I'm going to pass the root box and the depth, right? So we actually, I do need to pass these two things in addition to our two operative parameters, the box and the depth. So the box in this case is going to be the root box, right? It's going to be this one. And the depth is going to be, in this case, just everything, right? We're just going to, let's just do everything, right? So I don't know how many of these we have, but we know it's not going to be more than that because 2 to the 256 is more than like the memory in the machine, so it doesn't matter. So inside here, we just have two things. We've got the element width that we need. That's just these constants that we had specified, so that needs to go out here. We got the white bitmap that comes out of the command queue here. That, again, also come through. These, I suppose, only have to happen when we're actually outputting as well. And then we need to pass the group here and the solution. And in theory now, if I haven't messed anything up, this should still do exactly what it did before. It's just doing it recursively. Well, or it's not. So yeah, the if I messed anything up part turns out to be important. So let's see what's going on here. If the depth equals 0, what are we passing for depth? It's very high, so that won't happen. Or the box child count equals 0, which should not be the case. Then we come in through here. Otherwise, assuming we have children, we go through each of them. That should be right, shouldn't it? I couldn't tell you why that wasn't working, but it's definitely not working. Let's take a look at that. I'm gonna step on in there. I obviously did something pretty stupid, but sometimes the only way to tell what you did stupid is to just go on into the debugger and see what you did stupid. The debugger, or stupid finder, what happened there? Is there a reason that my breakpoint didn't hit? Oh, this is that. Okay. This is that new thing where Visual Studio 20, whatever this is, 2017, does not do breakpoints in the same place as it used to. It does them there. Yeah. I do not know what the deal is with that, but they decided to change that. So, okay. When we break here on this line, output letting points recurse. Let's take a look at what's going on here. So we're going to start at the root box index, which is set to box 0, apparently. Is that correct? So that doesn't seem right, because add box reference should have right. These are indirected. Yes. Always fun. So yeah, we have to actually indirect those. I never loved that, but yeah, we don't have any other way of doing it, right? We have to do everything through the box table. So both of those routines have to do that. See, I told you we would have got something wrong if we didn't visualize it. And we did. I think John Carmack is the person who said time spent making visualizations is never wasted. Something close to that. So I believe we have our utility function for this, so we really just have to use it. It's pretty straightforward. It's just that, right? So that's pretty easy to do, but we have to do that everywhere. So in here, we also have to do that. So when we go to get this one, we would have to do the same thing, right? So we need to do like a get box here. And then in our building routine, the same thing applies, right? Yep. All right. So in the building routine, the same thing applies, just making sure. So in here, for example, where we go to do our summation, when we do child box, we have to do a get box, like so. Right? I think that's the only thing that we did stupidly. Probably don't need to be in debug mode anymore, but let's just, yeah, so there we go. So what I want to do now is, besides turning us back to release mode build, what I'd like to do is I'd like to go ahead and figure out how to make the lighting drawn. This, now that I have a way of doing this recursively, I'd like to go ahead and make there be a way to control that depth, like with the keyboard, right? So I can sort of step down the depth and step up the depth to see what our multi-resolution lighting actually looks like, which, you know, would give us a little bit more of an idea of what's going on. So inside the lighting solution, I'm just going to have a little debug value here. And what I want to do is I want to make it so that when we do this depth here, I'm going to use debug box draw depth. And so what should happen now is that should be set to 0, right? Because we never initialize it. So when I do this, we should just have like the outer box, basically. It should be the only thing on the table, right? And what you can see here is this is the outer box, right? And we ideally want these elements to be bigger because the box itself is bigger, or we're never going to see it, right? So what I want to do here is I want to adjust this information, this element with element height, to be proportional to the size of the actual box, so that it makes some sense, right? So if we were imagining that it was 0.25 was the size that was correct for whatever those box sizes were, we want to make sure that we think about what that means. So it probably meant that those boxes were 1 point something long. I'm not sure how long they were. But we want to sort of have something that's going to be proportional to the box size. So what I'm going to say here is I'm going to say, all right, let's look at the box itself and how big its surface was. And that's what we'll assign these points to. That's how big the points will get assigned to be. So if we take a look at the box surface call, light box surface. So if we take a look at this guy right here, we've got the half width and the half height. What I'm going to do is just take those values and probably just divide them again by 2, right? Just to make them a little smaller than that. And that'll serve, for the moment anyway, as our understanding of how big we want these things to be. Now, I could also make it proportional how many lights there are, but at the moment I'm not going to. All right. So here's our root box, and so this encapsulates the entire lighting solution. And now what I'd like to do is be able to get sort of lower down into it. Again, if I wanted to, I could make this a little more accurate potentially by, again, using that light point count. So I could say something like, point count equals that, which is the number of points on the surface, and then I could say size ratio equals 1.0 or something. What do I really want to say there? So maybe 2.0 or 1.8, I don't know, something like that. And then I could say, well, if the point count is greater than 1, so there's more than 1 point, then we'll just divide the size ratio by that point count, because we don't really know what else we would do necessarily. It's probably not the best way to do this, but it's good enough for now. And then we'll just say that we have a size ratio that multiplies these here, and that's just our sort of poor way of getting some related size. And so now when we look at the box, we can actually see here's our thing. The white is not involved in the lighting solution because it's too far away from the visible area. There's our lighting box, which is what we would expect, right? And there's the summed amount of lighting. Now, the first thing that I notice here is the lighting on this box isn't fabulous. I don't know, maybe it's not as bad as I think. But there could be some bugs in here. It does correctly seem to give more weight to here, so you can kind of see that where the light is, it actually is a little bit brighter. So I don't know, maybe it's not wrong, but it does seem like over on this side it should be darker than it is, and it's not, so I'm not sure about that. Maybe we've got the weighting information incorrect here, or maybe something else is busted, but I think it's probably worth checking that a little bit and figuring out what's going on there, because it could be that something's busted. Now, we'll get a little bit more information about whether something is busted now as I go and add the ability for us to adjust that value. So what I'm going to do here is, along with where we have our F keys pressed, what we can do here is, again, add in some F key information, maybe F5 and F6, to allow us to step that lighting in and out. So here on the lighting solution, what we want to do is, what's that called? Solution? I don't remember. Test lighting. So what I want to do here is inside that test lighting, I want to take the debug box draw depth and I want to modify it. So if we hit F5, if this is greater than 0, then I just want to subtract it. And in the other case, I just want to add to it. And that's it. That's all I wanted to do. Oops. And now, in theory, what we should be able to do is use F5 and F6. So if I hit F5, nothing should happen because we should be at the lowest level already. If I hit F6, we should be able to see our next two boxes down, and then so on and so forth. And so what you can see here is, I definitely think we've got bugs in here because these don't seem like fair representations of the lighting, right? So if I toggle back and forth and you take a look at what lighting elements are being summed here, while this does look like a box that correctly encapsulates this, there's definitely some lighting here, and yet the lighting on this, well, yeah, it just doesn't seem to make a lot of sense, does it? I mean, those are the boxes that are included here, and somehow this box says that all of the things inside it have no light at all, but yet you can see that there's light in them, right? And so it seems like maybe we're only getting the emission value here and no reflected value at all, but we should be accounting the reflecting value from last frame, right? I mean, in fact, if you look at it, it's very clearly giving us that, because look at where the lights are. Here's the lights that are emitting. And when I go ahead here and start to put these together, you can see that the boxes that don't have emitters have nothing, right? So I think we've got a bug where we're only counting emission and we're not counting secondary emission, so transmitted emission. And so let's take a look at like what's happening there or why that's happening so that we can understand a little bit better. So when we're doing our recursive output, you can see we do accumulated PPS and emission PPS are the two things we add together here. And so what do we need to do, I guess, so that's probably the problem, since we're cold setting that. Well, I don't know if that's true. Let's go ahead and look. So we know that accumulated PPS is going to be nothing. We know that emission PPS is going to be whatever it started out as, right? So that explains the results we're seeing if emission PPS never got modified. Let's see what happens. So in here you can see that we sum our emission PPS, we sum our initial PPS here, and then I guess the problem is that's actually the value that we want to be drawing, right? It's the initial PPS that we actually wanted. So I think what we probably have to do here, and this sort of answers our question, is the accumulated PPS kind of has to be set to the initial PPS as well, I guess. Yeah, I don't know any other way to do it. And that, I guess, should draw more fairly what's happening here. So again, here's that initial box. Here's what we're looking at in terms of the lighting solution there. So there's the initial box. And let's go ahead and step down it. It does seem a little weird, right? I mean, it doesn't... It doesn't really seem like a fair average to me. Like, where is that light coming from? You know? Why is that suddenly pure bright? Is it because there's a light in there that's getting averaged all of a sudden? I guess that is why. So let's just see if it's fair if we don't draw that, because that's not really relevant, I suppose. So I guess what I'll say here is, let's not add that in. Unless this is a leaf box. Does that fix that problem? All right. That does not seem to fix that problem. Did I do that right? So when we're drawing the lighting points, we start with the accumulated PPS. If the child count of a box is 0, then its emission PPS is included. Otherwise, the emission PPS is not included, right? So you know, I can double check this by just saying, look, we never add it. It's just not even in there. Yeah, so in that case, we're still getting sort of the accumulated values themselves are blown out in that summation, which just seems weird, right? Because these are averages. And so especially when they're not taking into account that emission PPS, so something seems busted here. Let's see why that's happening. So everything that we sum is definitely multiplied by the weight. Right? The ref C, the emission, and the initial, they all get normalized. So I'm not sure why we would be getting that sort of aggressive over-counting there. I guess since, I mean, given that the value is so much higher, it's possible that it just is naturally dominating the average, I guess. But that doesn't... I don't know if I really believe that. You know? It seems a little far-fetched. I suppose part of it could be that maybe the fall off is too steep. I mean, we could try doing actual length. But again, I'm not really sure. I'm not sure what a good way to approach that would be debugging wise, because it definitely seems wrong to me. But it could be that I'm just misunderstanding something as well. It could be that they're just so bright they dominate the average. I could be willing to believe that. It's just I don't really want to assume that that's true and then have that turn out to be a bad bug that's in there that we're just missing, right? So I don't know. So here's what I'll say. We don't have much time left. I'm going to say that let's just assume we need to do a little bit more work on that still. So I'm not 100% happy with that. But that's okay. So what I'd like to do here is just go ahead and finish the part that I was going to say before, which is let's just go ahead and use that now and see what difference that makes. So here where we do if box child count, what we'll do is we'll say, okay, and close enough. Right? And so what we can do here is now introduce an expression to close enough that will make it so that we don't recurse if something is too far away. Okay. So here we're doing our lighting and we're doing it that way, where we always use everything. And now I'm going to just try adding in an expression that will make it so that we won't do that, right? So if we say that, well, okay, let's suppose that T-ray is less than some value is how we're going to do that. I don't know what the value should be. I have no idea. Let's say that the value has to be, I don't know, 6 meters or something like this in order for us to recurse. Now we should get a very different result from the system in theory, although I guess I don't actually know if that's quite far enough. But you can imagine us playing with this value now to see what the difference is. Okay. So let's see. Here's our total ray count. It's, array cast box count. It's 1 million, I think. I want to be able to see these at the same time. I can't really do that. This is where I want multi-monitor. All right. So it's 1 million-ish, right? Here's if it's just 2 meters away. There you go. So that drops it down. It doesn't drop it down as much as I would have thought, though. Let's put it back up to 10. So the effects are smaller than I would have thought they were, although that could just be because we're in not as big of a space. Like we're still, for whatever reason, this particular creation here did not really, didn't really create a very wide room. I could go through and, oh, you know why? We can make the room real big, actually. Can't we? So let's suppose I just do a screen index of 1, but I make the room like 32 by 32 or something. Does that work? I don't actually know if it does. Is that too many? We never really did the world creation stuff that we need to do in order to make sure that we can... Like, the world building stuff is still a bit busted. But okay, there we go. There's a much larger room. Oh, that's a very large room. So there's a much larger room. You can see the area that... This is the box that we've just arbitrarily set up for lighting. So the area outside it doesn't get lighting. And off we go. So at the moment, there's our raycast box count. I'm going to turn this off by just saying, oops, didn't mean to do that. Meant to just make it be true. And if I look at the total raycast box count here, which I think that is the thing that comes through here, right? We increment this every time through. Yeah. So if I crank that number down quite a bit, we should cast a lot fewer boxes, right? Well, I don't know about a lot fewer, but... So from 1.1 million... Why are we getting... I don't know why we're getting that. It's really annoying. So that number just doesn't decrease very much. So I feel like something weird is happening. Because I guess unless our spatial hierarchy is just maybe our spatial hierarchy is just really good. That seems like not true. I mean, this is incredibly... You can even see the results of how the lighting is very bucketed here. I'm surprised to see, because we know that well, I guess the fact that solution point count says what it says maybe has something to do with it. Point count should not be that number. Let's go look at that. Where is that value? Getting output. So what's happening here are... How are we getting that value? Solution point count should be a sane value, but it's not, right? I want to see what's up with that. So that's definitely bad. So the point count is 3,457, supposedly. Right? Yet we're seeing that value. What on earth is going on there? Do we have a bug in how we output U16s? Could be. Let's find out. Looks like it. Now, I don't know why, though, because the box count is also a U16, is it not? So that seems a little bit weird, but it could be because it's padded. So it could be that since there's another thing, in fact, I guess I can test that. So let's suppose that we did exactly that, and we said, all right, we're outputting the solution point count, and what we see when we go through here, so is this garbage value. Now we go ahead and pad it inside here, so we say there's just a huge gap of zeros in between there. Now what happens? Yeah. So there's definitely some problem with how we were doing that. We must cast to a U32 pointer somewhere in the debug interface for U16. So we're passing the pointer to the value. And I guess it must be choosing the U32 version. So I'm wondering here. Suppose I do this. So we don't have a U16 version. Yeah, so it looks like it's, because we don't have a U16 version, it's treating it like a U32, which is, you know, completely wrong. So we can make a custom version of one of these. And that would be like something like this, right? Oops. Where we had the like type of the thing and an as type, right? And then we said, well, the type of the thing is going to be one of these, and then, you know, we'll write it back by casting it. You know, your mileage may vary. What was the question? Macro redefinition. Oops, sorry. And when we set the type, it's got to be that one. So yeah, I mean, we can do that, and that's all fine. And that would probably just solve the problem. If anyone cared. I don't know that anyone does. But probably we work with U16s now. Hey, look. So for 3,457 points, and we're casting 16 rays per point at the moment, right? So that's 55,000 points, 55,000 initial rays. So 55,000 is like in this range here. So if I were to heavily restrict that distance, I would actually have expected it to be quite a bit less than that value when I do the raycast. And I'm not seeing that, which is just a little bit odd, right? So let's say I just force it to always hit the top one. What happens? Other than the fact that we crash in that. We should probably switch to using conserved DLLs so we don't have to worry about string preservation anymore. So how many do we cast now? Yeah, that seems really strange. So that means that we're in enough boxes just by default to have to iterate over that many children, even if I'm all the way out here in the corner. Right? And I just don't know what to make of that. But it sure seems like a bug. Like, if we're never recursing, then I don't see how we get that far down the road. Know what I'm saying to you? Because in theory, this is only happening if we're actually inside it. Maybe this check is wrong. Is this firing like way more often than it should? Because this should only recurse on boxes that we actually are inside. Where the thing that's casting the ray is inside the actual box. And so that, if I'm out in the corner, that should only be accounting for a very small number of actual boxes involved, right? And we could test that if we wanted to. But just like, yeah, you know, if we look at how many things we'd have to expand, it'd be like the only box that we'd be inside of for any given point, it just seems like it would be, well, we know it would be 4. But I guess it includes the whole path downward. Maybe that's enough to make it like 10. Because if it was 10, then I guess that's where you get that multiplier 4. Well, what am I saying? Look at the total ray count. It's huge. Yeah, okay. Let's investigate this further. I'm obviously confused about how this is working, which is not good. So let's investigate this a little bit further, and I'll just return it to its original state. So this is just doing the same old lighting, no changes. How many rays are we casting? Like how many rays are getting cast here? So when we look at total ray count, here's the number. So that should be the ray count, like, you know, what we would expect to see, or what I'm expecting to see, erroneously obviously, is that's the number of points we have, right? So the number of points then needs to, each one of those is going to get cast 16 rays, right? So I would expect 55,000. So obviously I'm thinking of the ray count wrong. Why am I thinking of the ray count wrong? So here we are. Let's take a look. Here's our sample set. Here's our ray count. So for each sample point, which is point count wide, we're going to do that many rays. Yeah. Sample the hemisphere, call the raycast, do this, and then we're supposed to exit, right? So how could we get anything other than sample point times ray count? Like, how do we get something else out of that? And I guess the answer is because of the recursion. So we should probably change this. This total ray count is a little misleading. That's really not what that value means. So raycast point count would really be the thing. Let's rename these better. So here's what we're going to do. We're going to have a maybe total ray initiated, let's say. So like this is how many we're going to start, or like total casts initiated. Then we're going to have total cast recursions. And then we'll have total boxes tested. I don't know why these are to-dos. These are notes. Okay. So these are what, let's just clean this up so we're not confused about the statistics we're actually looking at, right? So in raycast recurse, we're talking about total recursions, right? Total boxes tested is in here. And then we could further split that, actually. So we could call these total partitions tested and total leafs tested. We could do like these as two different values. So we could say something like total partitions used and total leaves used, or something like that. Well, I'm not sure how we want to do this. So in here we could just say, well, all right, you know, if box, you know, child count else, right? So we'll say this is the total number of partitions we tested. This is the total number of leafs. Probably should say leaves. And then we know the total number of recursions is the number of like steps through that. I don't know that we actually do we care about that value? That value seems irrelevant. Like, who cares? I don't know that we care about that, so let's get rid of that. So I think that's mostly what we want. And then in here we'll do solution total cast initiated plus plus, because that's how we know we initiated a cast. This will not have any summations in it at all. And then we will just update this to reflect that. So inside lighting test, we'll do total casts initiated, total partitions tested, and total leaves tested there. Total casts initiated, total partitions tested, total leaves tested. All right. Ooh. I did that wrong. Sorry about that. I meant to do this. Total cast initiated, total partitions tested, total leaves tested. And let's see if I can look at these stats and make more sense of them now. All right, so 55,296 casts initiated now is exactly what I would have hoped, right? So at least we now know that that value is sane. Total partitions tested tells us how many boxes we're checking that are not actual leaf boxes, right? And that says that we're doing 857,000 of those partition checks, which is really high, right? So what I would now expect is that if I were to, I would have expected myself to be able to reduce the number of partitions tested by doing that early out check that I was saying before, right? In other words, if we go through here, by the way, what's our profile say here? 67. So actually, this is still really fast, which is kind of surprising. But anyway, whatever. So that total partitions tested number being very high. Again, that just seems like kind of a bit of a weird scenario, because I would have expected now when I go through and request a smaller number of those that we would have seen more of an effect on the numbers, but we weren't really seeing more effect on the numbers, and so that's the part that's a little confusing. But anyway, so if we go ahead and look at raycast recurse now and come here and actually do force it so that it's never going to recurse on anything other than the box that you are physically inside, right? I would have expected total partitions tested to go down quite a bit, but actually total partition tested hardly went down at all, which suggests to me that for most people, most of the boxes tested are ones they are inside. And I just don't understand that. It seems almost like there's a bug in this check or something, because it just doesn't, you know, it doesn't seem like you could be inside more than half of the partitions you checked. I mean, if anything, the definition of where you are for a point, it can't be in less than half the boxes, right? I'm sorry, in more than half the boxes. How could it be? It can only be in half of them if they're split binary, even the best case scenario where you only had one split. You can only be in half, right? But it should be drastically less than half if you go down more than 2 splits worth. So that seems busted, and I'm kind of wondering if, like, is in rectangle center halfdim somehow wrong? Because that's pretty strange. So let's think about this for a second. So the box radius, let's take a look at that function. I mean, it looks pretty sane. We're subtracting the ray origin from the center of the box. Pretty reasonable. And then you're seeing whether the absolute value of the result is less than the radius on all axes. So, you know, if the distance in question there is less in each case of the x, y, and the z, then you're good. Certainly seems right. So I guess we'll have to leave this for tomorrow, and that's fine. But I mean, again, totally possible it's correct. Just doesn't seem plausible to me in that way. So take a look at the number of leaves tested as well. So the number of leaves tests that there are, right? 209,000 in this case. So we go in here and now we say, all right, now you can test like way more leaves, right? Test them all. Go all the way down, right? Total number of leaves tested doesn't even double. It just seems odd. And so I feel like I really want to dig into that code a little bit and find out if there's just something fundamentally screwed up happening there that is making us test in a way that is isn't congruent or isn't what we would expect, right? Because you would expect a pretty large number of leaves to be no longer tested in that scenario. That just seems real weird. I mean, I guess, you know what it could be is just that most of the time the angle that you're testing just hits the skylight. In which case you just don't recurse. So I guess I could believe that. In this case, you know. And especially, I suppose, you know, maybe if I go in and add, if I allow it to add another layer on top. Let's see here. We have a lot of like extraneous room here, so let me try to make that not so big. So if I hopefully here can add, you know, I want room like on top of me, so let me. That looks like it's always sideways, so can I set the direction to always be like one way? There we go. So now there's like more stuff in there, right? And you got people bouncing between these two. You know what, I might want it to go the other way, so let me make it stack on top. So now you've got at least like a lot less hitting the skylight in this case. And so if we take a look at that value here, I wonder if it changes significantly now, depending on that piece of information. So if in here we were to say foreclose this, and we're looking at, you know, I don't know how many 730,000 leaves tested there, and I say, okay, let's stop doing that. Does that go down? That's really annoying me. Does that go down? And that goes down quite a bit more, right? So that's a little more plausible there, I guess. When you say like, look, don't even really do raycasting, sort of do completely fake. So I could believe that was a little bit more plausible. Let me go ahead and see what happens now if I put in like a fair check of some kind. So I say like, okay, you know, it's 5 meters. See what happens to the lighting now. And that actually works pretty well. I think actually, in terms of compartmentalizing it. Yeah. All right. So it may be that that's okay. I still want to go a little bit more in depth on that because I'm just not 100% certain that I'm really getting what I expect there. So you know, I would like to get a little more information on that. I also want to know. So is this a reliable crash case now? So if I will this just crash? It doesn't always crash, unfortunately, because I was going to say it would be nice to go fix that crash, but it looks like it's a little bit less reliable than that. All right, so let's go ahead and go to a quick Q&A here, and then, yeah. Let's see. Oops. What's going on? Did that work? Yeah, that worked. Jimoflo, can you explain why the debug was... oh, yeah. Yes, I can. Sorry. Since we were in the middle of the lighting, I didn't take much time to explain what I was doing there. So, the way the debug system works, obviously, since it's kind of like an annotation system that sits on top of things, what it does is when you come through the debug system, you announce to the debug system the data that you wanted it to look at, and it looks at it. But we only have in the debug system a few different types that it handles, and you can see them here. And you can see that there is no, U16 isn't a type. It doesn't have 16-bit integer support. It only has like 32-bit integers as a thing, unsigned and signed, right? So what was happening before was that when you passed a U16, it would just find the closest match to the overloaded functions. And you can see there's a macro here, actually it was this one, that we just used to make a few different versions of the routine that picks up a value for the debug system. It would use the U32 version, or it may have used the Sign32 version actually based on C's integral promotion rules, but that's neither here nor there. Point being, it would use a 32-bit version. So what it would do is it would call one of these routines that had, say, S32 in here. which means that when it went to do the value, to pick up the value right here, this line right here, or this line right here. So it either wrote back if you were doing modification with the debug system, or if you're just keeping it, right, which would be this case. So if you're keeping the debug value, it would go, okay, into the event, store the value that I got, but change it to the type that I'm pointing to, that I said I was, which would be a U32 or an S32 in this case. That meant that it picked up not only the 16-bit integer that we're talking about, but also the next 16 bits that were there. Now, in the case of certain elements of the system, like box count, that's actually fine, because the next thing is a pointer, which is 8 bytes long, and C's padding rules for structures is that if you have a thing that's, say, 2-byte aligned, like a 16-bit integer, followed by something that's 8-byte aligned, like a pointer, pad out to the next 8-byte boundary. So there actually would have been 6 bytes worth of zeros following the box count here. So when we output it, we would just get 0, and even though it was taking a 32-bit or 4-byte slice of the data, it was fine because it was padded with 0, so it still looked like the right value. On the other hand, down here, what happened was, when I had the point count, I then added another U16, which is the extended point count, so we could track that value. That meant that there were 2 valid 16-bit values next to each other, which meant that there was no pad anymore. There was a pad previously when we had this, now there's no pad. What that means is the debug system will take 4 bytes. The next 2 bytes after the first 2 bytes actually had data in it, which would give it the wrong 32-bit value, right? So the only thing we had to do to fix that was just to make a version that actually respected the 16-bit value. And you can see that I did that here. So what I did is I said, look, let's actually use the 16-bit value correctly and just have the processor upconvert it inside a register, which is what's happening here, so that it just expands out with 0 padding and does what we wanted to do in the first place. So that's all I did there, was allow that conversion to work properly, if that makes sense. How likely is a lighting system GPU port? You could definitely run on the GPU. I don't know that we want it to. I'm not sure how to make that decision exactly. It may be smarter for us to just do a multi-threaded CPU version. It might be that that's just fast enough, but I don't know. It's pretty hard to say. Grimfi, off topic, did you ever find out if it's necessary for CPUs to have named registers? No. I'm still really curious to know if that's true. This is one of those things that's just like, I wish I knew someone who was really, really good at hardware design so I could ask them, because it's the kind of question that only an expert, extremely good, extremely smart hardware designer could answer, right? Because the orthodoxy is one thing, and then knowing whether the orthodoxy is just because of historical precedent is another, right? And it's a very complicated question with a lot of details, right? And so I don't really know. I don't have a gut feeling either way. What I can say is that it makes obvious sense to me why named registers came into existence and why they persisted for a long time. What I don't know is whether they still make sense now that CPUs are so overly complicated, right? And I don't know. And there were computers way long ago in the era where I think named registers were the right decision, obviously, that didn't use named registers. And at that point, I can understand why those machines didn't find favor. I don't think it was accidental that that wasn't the preferred method. But nowadays, I don't know if the same thing is true. However, I also don't see anyone proposing this. So I'm guessing that either that just means that it's just stupid, right? And if you're a really good hardware designer, you know it's dumb, in which case I really just want someone to walk me through exactly why. Not cursorily why, but really why, because cursorily I don't think there is a reason why. I think there's only a reason why when you really get down to the nitty-gritty, right? Or that it's just something that's too far from the current designs and you don't want to take a risk on doing that new design, right? I see someone in the chat brought up the Mill CPU. Mill CPU still uses named registers. They're just named based on their frequency of use, right? So it's still basically a named register machine for all intents and purposes, because you still have a limited number of names and they still are specific to what's happening inside the CPU. So they don't correspond to memory. And that's the key difference that I was talking about. I was basically asking, is there a reason why we don't have register to memory correspondence in modern CPUs? Because everything else does, right? So nowadays, like every last thing in the CPU actually does correspond to a memory location, except for the registers, right? So like the level 1 cache, for example, knows exactly where that thing would live in memory if it was to be put back, right? Registers are the only things that don't know that. And I don't know if that's actually the right decision. The argument for why it's the right decision makes a lot of sense in the old days. I just don't know if it makes a lot of sense now. And I suspect that the argument, so it may be that it is the right decision now, but the argument should look totally different than it used to look, right? So that's all. Long Boolean, do you think arranging pixels on LCD monitors in a blue noise pattern would be an improvement visually? So the answer is that it would absolutely be a huge improvement visually, probably, if you knew what the pattern was and the GPU used it for sampling, if that makes sense. I don't think you can scatter pixels in a blue noise pattern and then render to them as if they're square. That may be a problem. Now, if the monitor is dense enough, it might not matter. But then again, if it's dense enough, it might not matter at all, right? Right? After enough, memory is slow. Yes, I know memory is slow. That really doesn't have anything to do with whether your registers know where they live in memory or not, right? All right, I'm going to go ahead and close down. All right, thank you everyone for joining me for Notes on Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow the series at home, you can always pre-order the game on handmadehero.org. And it comes with the source code so you can play around with it yourself and do your own experimentation, which is a good way to learn. I will be back here tomorrow to work on more lighting. Until then, if you want to play around with the lighting yourself, you can let me know what you find. Hope to see you back here tomorrow for that. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.